This is another problem, an opener that will help you get you ready for the test. We've got a graph of f prime, and it has this graph. The f prime graph has horizontal tangents at -3 and positive 0.2. Now, before I answer all of these, I'm going to just go through and justify. And it didn't ask me to do that, but I'm going to. It's good practice, and I think a lot of times when we're given a graph, it helps us know what to look for. Okay, so we're going to justify using calculus. So when is f increasing? Well, that would be when the derivative is positive. When is it decreasing? Well, that would be when the derivative is negative. The critical points are where the derivative is either undefined or 0, but of course in this nice smooth graph we don't have any undefined spots. So we're going to look for where f prime is 0. Next, does f of x have a local maximum? Well, maximums occur when the function changes from increasing to decreasing, so the derivative changes from positive to negative. And therefore a local minimum occurs where f prime changes from negative to positive. So now let's go back and actually just write down where these things happen. So the derivative is positive from 2 on, so 2 to infinity, the function's increasing. It's decreasing, you got to be careful here, from negative infinity to -3, and from -3 to 2, because at 3 the function is not decreasing because the derivative is 0. The critical points are going to be x equals -3 and x equals 2. The local maximum would be where the derivative changes from positive to negative, but that never happens, so there isn't one. And the function has a local minimum when the derivative changes from negative to positive. That occurs at x equals 2. So same graph, but let's again go back and justify here some concavity things. Well, you're concave up when the second derivative is greater than 0. Now we have a derivative graph, so I want you to think. If I tell you a derivative is positive, you know the function is increasing. Well, kind of sliding that down a little bit, you know that if the second derivative is positive, its function, meaning the first derivative, is increasing. Okay, so that's what we're going to look for, because I don't really want to draw a second derivative. I want to just use what I've been given. Well, inflection points occur when the second derivative changes signs, meaning its function, the first derivative, changed from increasing to decreasing or decreasing to increasing. I'd rather say it's where f prime changes direction. Let's do that real quick. So we're concave up when f is increasing, f prime, so from negative infinity to -3. And it's decreasing here from, I guess we gave you 0.2, so from 0.2 to infinity. Inflection points occur when the derivative changes direction. That occurs at -3 and 0.2. Okay. Where's the absolute maximum and minimum? Well, when we see this, we should be thinking candidate tests. So we should be thinking of plugging in endpoints, plugging in critical points. It's a little bit harder when you don't have a function to just plug values into, but we can do some reasoning here, I think. First of all, we classified 2 in the last slide as a minimum. So let me just write that. This is a minimum. Negative 3, of course, is neither. So I think at this point you could almost rule this out. If it's not a local max or a min, it's not going to be the absolute max or min. Okay. Now, going back up here to the derivative, if I bring it down, since the derivative is negative here, that means the function is decreasing. So the function, if I could just kind of sketch it, it starts off, it kind of goes down, little level spot right here, and it goes down, it goes down, it goes down, it's decreasing, it's decreasing, it's decreasing, 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 all the way to 2, and then it starts increasing to 3. So what I just drew a quick sketch here, but what I wanted to point out is that this is a maximum because everything around it is below it. So this is a max. And at 3, we're increasing up to this endpoint, so it's a max again. So, yeah, we couldn't plug it in like the normal candidate test, but we found the absolute minimum because there was only one minimum. In the entire graph, there's only going to be one minimum, so it must be the absolute. And we don't know its value, but we know it occurs at 2. Now, in terms of the absolute maximum, I think we can make a real nice case that it's at negative 4. And your reasoning here would be the fact that the function decreases so much and for so long. And while it does increase at the end, it doesn't increase enough to bring it back up to where it started or higher.